Already started. Make sure this is in focus. Yep, it looks okay. What can I do for you? Any questions?
Wanted to look at the homework.
All right. The WebAssign homework?
Yeah,
All right.
I think it's 5.3 that I had questions about. Yeah, it's 5.3.
Okay. Let's take a look at 5.3 and I'll share my screen. Okay. So which problem are you looking at?
I think it's the one all the way at the bottom. I have mine up.
Let's see. There aren't that many. There are, what is this, three problems there?
Um, it's okay, yeah, it's for the sequences that they have where the number 6 is an example.
Oh,
I'm not sure if that's it.
this is 5.3. Let me go back. Maybe you're thinking about
Oh, I'm
5.2.
sorry.
Don't worry.
Yeah.
No problem. Number 6. Okay. So we did discuss this, did we not discuss this one? Or maybe it was discussed in an office hour, but we can discuss it again.
She was with me on Friday.
Yeah, Sunita, we did discuss this in that special pop-up office hour Friday morning. I did post those notes and everything, didn't I, Sunita?
Yes.
Okay, but
Okay. Oh,
we can
oh.
discuss it again. Was there something in
Um,
particular that was making you wonder about this one, or was it the whole thing, or?
No, I just didn't recognize the math, but since you have it, I can kind of just wait and listen to whatever Sunita has to ask, and I'll bring it up and look at it because I didn't know that it was there.
Okay. Yeah, you have to guess a formula, but if you look at the first few terms for like n equals 1 and n equals 2 and n equals 3, you can guess what that product turns out to be. All right, so I'll stop sharing. Sunita, do you have a question?
So can I look at the 5.3?
Yep,
Mm-hmm.
we sure can. Let's look at 5.3. Which number?
So I haven't started, but it's look like any.
Well, that's not the way it actually should work. You should have tried some of these, and then if you have a
So
question.
yeah, I'm going to start today because the day is
Okay.
tomorrow, so
Well,
that's why.
by the way, this particular problem, number one,
Let me
is
see. Mhm.
just like, am I sharing? Am I sharing the screen?
Yeah, I can say that.
All right, share the screen. Okay. Num, ah, 5.3. This is stupid. I don't want to get where all the answers. All right. So the very first question in 5.3 is, I don't know if you can see it. Let me see if I can make it bigger. This is a problem very similar to the very last problem that we worked in class.
Okay.
And it is to prove the following statement that for every integer n greater than or equal to 0, 7 raised to the n minus 1 is divisible by 6. We proved 5 to the n minus 1 is divisible by 4 in class. It turns out that x to the n minus 1 is always divisible by x minus 1 for any integer x greater than or equal to 3. So it's a whole class of true statements. So the first thing it asks is to show that p at 0 is true because we're asked to prove it for n greater than or equal to 0. So our lowest level value for n is 0. So here it just says select p of 0 from the choices below. Well, there are different ways to write that 7 to the n minus 1 is divisible by 6, whether n is 0 or n is just n. As you look at these 4 choices, which one of these looks like p of 0 to you?
It's like this plus 6 by 6, so 7 and 1. So is that the last one?
Is it? Okay, let's talk about it. The statement is that 7 to the n minus 1 is divisible by 6 for all n greater than or equal to 0. Okay, that's the claim. So let's just remember what our notation is. This is the same thing as saying 6 divides 7 to the n minus 1, right?
Yes.
And we have a notation for that. 6 divides 7 to the n minus 1. And if you go back and look at class notes, that's the way that we wrote the statement that we proved as our last induction proof. I rewrote it like this.
Okay.
I think I wrote 4 divides 5 to the n minus 1 because it was a 4 and a 5 here instead of a 6 and a 7.
Okay.
So if these are all different ways to say p of n, okay, then what is p of 0?
P of 0. The It's the end, right?
Yeah, the n is being replaced by a 0.
So 7, it's a 0, power 0.
What about it?
So minus 1.
Okay, that expression
Mm-hmm.
is divisible by 6. So that means 6 divides into that expression. Do you see what I mean?
Yes.
So you have to dig into your notes. You have to dig into your notes about divides, and it would behoove you to look at class notes because there's a reason why in class, there's a reason why we proved that 4 divides 5 to the n minus 1 for all integers n greater than or equal to 0. I picked that example to work with you because I knew that I wanted you to learn how to do this, and I knew this would be one of the homework problems. Does that make sense?
Yes.
So go back and look at those notes, and it should help walk you through this WebAssign 5.3. Okay,
Yes.
I do plan things.
Thank you.
You're welcome. Are there other questions? Shall we look at the next one?
Let me go ahead.
Look at the next one. Oh, the next one is an interesting algebra problem. And that is that 5 divides 7 to the n minus 2 to the n for all n greater than or equal to 0. It's an interesting algebra problem. And they show the algebra trick in the inductive step. But the first thing they ask us to do is just select the statement P of 0 from the choices below. So which of these choices do you think would be P of 0? That's just, this statement, but instead of N, there's a 0 here, and there's a 0 here. Well, you have to understand what our notation tells us when we want to express 7 to the n minus 2 to the n is divisible by 5. You need to understand that we write that like this. This is the same thing as saying 7 to the n minus 2 to the n is divisible by 5. Saying 5 divides 7 to the n minus 2 to the n is the same thing as 7 to the n minus 2 to the n is divisible by 5.
Yes, sorry, I was on mute, sorry.
I'm sorry, what?
Uh, oh yeah, I was on mute, sorry. I talk about it. I just say there
Oh,
was
I
some
didn't realize. Okay, good. Good. But this one is an interesting algebra problem because the induction step is to show for each integer k greater than or equals 0 that if p of k is true, then p of k plus 1 is true. Of course, the setup for the inductive step is always the same. We'll let k be any integer with k greater than or equal to that bottom level value, which is 0. And suppose p of k is true. Select p of k from the choices below. So here's p of n, that 7 to the n minus 2 to the n is divisible by 5. Which one of these would be p of k?
the is that the last one?
Yeah,
Mhm.
bet. We assume that. Now, we must show that p of k plus 1 is true. Select p of k plus 1 from the choices below.
Okay. 7k plus 1 is power, so minus. Is that the first one?
That's
PF.
right. That's right. That's the first one. Now, the interesting thing is our inductive hypothesis, P of k says 7 to the k minus 2 to the k is divisible by 5. Well, that translates into an equation that 7 to the k minus 2 to the k is a multiple of 5, 5 times r for an integer r. Do you agree
Yeah.
that this is the equation that our inductive hypothesis gives us? Remember what we wish to show. We wish to show that 7 to the k plus 1 minus 2 to the k plus 1 is divisible by 5. So we're going to look at 7 to the k plus 1 minus 2 to the k plus 1, and we're going to try to transform that, rewrite this somehow, so that we see a 7 to the k minus 2 to the k. The minute we see a 7 to the k minus 2 to the k, we can extract that somehow from 7 to the k plus 1 minus 2 to the k plus 1, then we'll be able to substitute in 5r for the 7 to the k minus 2 to the k. Then maybe we'll be able to write 7 to the k plus 1 minus 2 to the k plus 1 as a multiple of 5, as 5 times some integer m. So check out this interesting algebra. 7 to the k plus 1 minus 2 to the k plus 1 can be rewritten. 7 to the k plus 1 is the same thing as 7 times 7 to the k. Do you agree?
7 to the k, yes.
And 2 to the k plus 1 is the same thing as 2 times 2 to the k. That's the first step. And then we realize, hey, 7 can be broken up to
5 plus.
5 plus 2.
Okay. So,
And then there's some algebra that we can do from this stage. I'm going to write a few things down. For the inductive step, we assume P of K is true for some integer K greater than or equal to 0. So we assume 5 divides 7 to the K minus 2 to the K. And that translates to an equation that 7 to the K minus 2 to the K is 5 times R, where R is an integer.
Excuse me, Professor, we can't see your pad. We just see the shared screen.
All right, so this is what we just looked at. Okay, and this is our inductive hypothesis right here. This is what P of K turns into. It turns into this equation. But what we wish to show is that P of K plus 1 is true. Let's actually look at what that means, i.e., we wish to show that 7 to the K plus 1 minus 2 to the K plus 1 is equal to 5 times, say, M, where M is an integer. Do you agree that that is what P of K plus 1 says? Do you agree that that is the statement P of K plus 1?
yes.
So the deal is, we want to say something smart about 7 to the K plus 1 minus 2 to the K plus 1. We want to get it to look like this. We have this equation that we want to be able to use somehow. So the interesting algebra work entails somehow extracting a 7 to the K minus 2 to the K out of this and hoping that there are 5s in everything else that's left. Let's take a look. Let's look at 7 to the K plus 1 minus 2 to the K plus 1. Well, the interesting thing is that is 7 times 7 to the K minus 2 times 2 to the K. Do you agree? Starting with the left-hand side of P of K plus 1.
Mhm.
All right. Now we're a little bit closer. We're a little closer to seeing a 7 to the K minus 2 to the K. At least we see a 7 to the K here and a 2 to the K, but we only want one of each. Well, we can rewrite 7 as 5 plus 2. Now, how is it that we know to do that? Well, the way that the kind of the interesting thing is we want to see some 5s, right?
But there is like 7 minus 2, so maybe like
Yeah, yeah, we want to see some 5s, you know. And when we break up 7 to 5 plus 2, it introduces a 5. Okay, so let's just take a look at what we've got. We've got 5 times 7 to the K plus 2 times 7 to the K minus 2 times 2 to the K. Just distributing the 7 to the K across 5 plus 2 like this. Does that make sense?
yes.
Remember what we're shooting for. We're trying to factor a 5 out of this whole thing somehow. Well, we got a 5 here, but we don't have a 5 here or here yet. But we'd sure like to be able to use this. Okay, so this has a 5 in it, so this is good. Somehow, we have to realize that the 7 to the K minus 2 to the K is in here if we factor out something. What should we factor out of this and this?
2,
Yeah. We take the 2 out. Then what's left?
7K minus K, 2K.
Good. And now, suddenly, we do see the 7 to the K minus 2 to the K. And we'll be able to use our inductive hypothesis.
Yes.
So
Yeah.
now we say, hey, by induction, if we were going to write the proof properly, we'd say this is 5 times 7 to the K plus 2 times
7.
5R, because 7 to the K minus 2 to the K is equal to 5R. So we put the 5R right in there. You see it?
Yes.
And now we're just one step away from showing that 7 to the K plus 1 minus 2 to the K plus 1 equals 5 times an integer m. What is the integer m?
It's
Okay, we're going to pull a 5 out of here and out of here.
it's
What's
going
left?
to be
Yep, 7 to the K, good.
2, but
This is 2 times 5 times r.
2 times 5, 10 is
But we're pulling out the 5, so what's left? If we factor out the 5,
uh it's 2 times 5. It's 5.
we're taking the 5 and factoring it out here. See, this 5 is coming out here, just like it came out there from here. Is this confusing with the box around it? Would it
So
be just better if I just wrote it's 2 times 5r? Would that make it easier? This is 2 times 5 times r. What is left if we factor the 5 out?
it's like R.
Yeah, 2 times the r. That's our integer m, is 7 raised to the k plus 2 times r. Okay?
But
This is an integer.
uh,
Do you understand?
yes, I understand that one. The last one, the only confusing the like is there is like on the top 7K plus 2
7
R.
raised to the k. It's not 7k, it's 7 raised to the k.
Mhm.
Okay. All right. Just want to make sure. So what are you trying to put that into WebAssign right now while you're talking to me? Anyway, that's what they're trying to get us to do. They're trying to get us to see that there's some algebra that we have to actually do to finish the problem. They say continue simplifying the right-hand side. So, they leave it at this. I've just showed you how to do the rest of it. We simplified, we applied the induction hypothesis, and express the results in terms of K and R. So this part right here that goes in the box is what we were calling M.
Mhm.
Does that make sense?
Yes.
Cool. It's an interesting problem because of the algebra.
Yes.
Problem 3, we worked in class.
Mm. Mhm.
Excuse me, Professor.
Yeah,
Can we look at problem 5? Because I worked it. I thought I did it right, and I did not get it right. It's a pattern of it's 4 plus 8 plus 12 plus 16, and we're supposed to find the sum given below of these integers.
Yeah, are you back in section 5.2?
Yes, I'm sorry.
You're fine. All right. So it's section 5.2, number 5. Is that what you're telling me?
Yes.
Sure. Let's get to it. So do you want to just read it to me?
Yes, it's use the formula for the sum of the first n integers to evaluate the sum given below.
All right, give me the sum.
The values go from 4, the pattern is 4 plus 8 plus 12 plus 16 plus dot 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 all the way to 240.
Okay.
And I factored everything by 4. So I had 4 open bracket 1 plus 2 plus 3 plus 4 all the way to 60. And then I thought, okay, so I multiplied it by, I took the number less. So I think I did, what did I do?
So n is 60.
Uh, yes.
So this is 4 times, just use 60. 60 times 60 plus 1 over 2. But don't forget to multiply by 4.
Oh, so, okay, I see what I did wrong. So this is like P of k plus 1, where we multiply 60, that would be our k, by 60 plus 1, that's our k plus 1.
Not really. Yeah.
Mm.
Sorry. This isn't an induction proof. It's just simply using a formula.
Oh,
But this is 1 plus 2 plus 3 plus dot 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 up to n equals 60.
this have been done with 59 times 60?
No,
Oh,
that would be right if we ended at 59.
oh,
Formula is n times n plus 1 over 2, not n times n minus 1 over 2. You might have your formula wrong.
okay, oh,
I did that once. I taught one day I was teaching it and I had the wrong formula. I put n times
oh.
n minus 1. Yeah, it doesn't work. But it's n times n plus 1. Remember, if we try to actually remember what I was telling you this the story about trying to add up 1 to 100. Did I tell you all this story about Gauss? Gauss was at school back in the days when only boys could go to school.
I
And
don't think so. I don't
back in the
remember.
days when they wrote on slates, like a little broke, not even nice, like a little blackboard piece. It's not even nice ones, just like old, really like rough pieces of slate and, charcoal or chalk and gypsum or something. And it was really hard to write. Like paper was at a premium. People didn't have paper. Ordinary people couldn't afford paper. Anyway, so a Gauss, who's a very famous mathematician, schoolmeister, put them all to task and told them all to add 1 to 100 because he was thinking, oh, that's going to take them forever because they've got this little, like this small slate. It might be half the size of this, but they'd be like 1 plus 2 plus 3. Maybe they get a few numbers there and they'd like add those up. And then they'd have to put that there and they'd have to erase that and then put plus 5, plus 6, plus 7, right? And he was thinking, oh, this is gonna, what is this, 11, 18, what, 28, and then they'd have to, put the 28 here and erase that and then add, 8 plus 9. He figured it would buy him an hour of time. But what Gauss did was he realized, well, it doesn't matter what order I add these numbers up in, it doesn't matter what order. So he took the first one and added it to the last one. Then he took the second one and added it to the penultimate one. They're all 101. And he realized, oh, if I add them up this way, I get 101 every time. So how many pairs are there? 50 times the 101, but 50 is 100 over 2. So this formula.
Wow.
I know, right? He did it when he was like, I don't know, 9 or something. And the story goes that the Meister was actually the clergyman. The church offered school. No. His father, Gauss's father, was a clergyman, and he didn't have much money. So the Meister went to his father and said, "Hey, your son is really smart. He's smarter than I am. I really can't teach him much." And the whole town pitched in to send Gauss to university, like a proper
Wow.
school. Uh-huh. And he became arguably one of the most famous mathematicians who's ever lived.
Wow.
I know. Isn't it cool? But that's a way to remember it's one more because these add up to one more than 100. It's 101. Yeah.
Ah.
And the 50 is the 100 divided by 2. 1 to 100. N is 100. So 100 over 2 is the 50 pairs. When you add them up, it's the biggest one plus the lowest one is one more than the biggest one. And then me. And then me. I just think it's brilliant, that the kid figured it out. Anyway, that's the way the story goes. Oh, you got a story. Who knew you'd get a story tonight? Other questions? I do have measure 2 material for chapter 6 going up. Are you okay with your induction proofs? In fact, that's the next thing I want to do is I want to sit down and try to grade those so that I can turn them back. Let's just talk a little bit about proof by induction, because if anybody reads these notes, I would like one thing to try to teach people is how to format their proofs by mathematical induction a little better than they're doing, just for organizational purposes. And it's sort of like a skeleton idea of how a proof by mathematical induction will generally look. We always say proof by the PMI or by mathematical induction. And then, we always say, let P of n be, and then, whatever it is, Then there's a basis step. And the first thing to say in the basis step is to tell your reader what the lowest level value is for this integer n. We call that lowest level value n naught. And then here you just write whatever it is, And then the wish is always the same. We always wish to show that P evaluated at n naught holds true. It's always the same wish in the basis. And then we always look at the left-hand side of P of n naught and we show work, show the work. And then the right-hand side of P evaluated at n naught, and show the work. And then we get the left-hand side equals the right-hand side. So P of n naught is true. And that's always the way the basis step would go. Even if it's a divide statement, there is an equation that we're trying to prove. And this works really well for the sum formulas. And then when we work on the inductive step, we always tell the reader what K is. Let K greater than or equal to n naught, whatever n naught is, be an integer. And we always assume something. What do we assume in the inductive step? What do we always assume?
We assume that P of K is true.
Exactly. Assume that P of K is true. And then we write it, i.e., assume, and then we actually write it. And I like to put a box around it, and P of K's in there so we, have our eyeballs on it. And what do we wish always in the inductive step?
We wish to show P of K plus 1 is true.
Exactly. And we always, want to actually, write down whatever that looks like. Because man, if we don't know what it looks like, how in the world are we going to prove it? So it's always the same assumption. Assume P of K. We wish to show P of K plus 1 is true. And then usually we start with the left-hand side, even if it's an equation, and then we work on it. And somewhere along the way, the algebra, a lot of times we break off the K plus first term if it's a sum or a product. If it's not, we're looking to somehow do the algebra like we looked at tonight with divides, do the algebra so we can see what somehow the inductive hypothesis equate, we can see the left-hand side of P of K somehow in here, we see maybe it pops up here, and then we make the substitution, using P of K. And then we do some more algebra, and finally, we get the right-hand side of P of K plus 1. And then finally, we invoke the PMI, we always say by the PMI. We can now say, whatever it is, P of n whole, whatever that statement is true for all n greater than or equal to n naught. I mean, this is kind of like a skeleton of the way that we prove induction in general. And you can get lots and lots and lots of credit just for doing the stuff that's really easy, like, state what your, P of n is. Make sure you tell your reader what n naught is. Almost everybody should be able to prove the basis step. Just don't start with the equation you're trying to prove. You got to work separately on the left-hand side and the right-hand side. People should be able to get lots of points for setting up the inductive step by telling your reader what K is and using, the word assume. P of K is true, and writing P of K. At least show me you know how to write P of K. Write your wish. You'll never get downgraded from your wish, but you can get points for having the right wish, even if later on, if the algebra is an issue, you at least show me you know what you're trying to do, even if you don't do it perfectly, right? You should be able to start with the left-hand side. You should be able to break off the term. You probably should even be able to perform the inductive step. But even if you have some problems, with the algebra, you could just say, hey, at least I know I'm trying to get whatever the right-hand side of P of K plus 1 is, and then invoke the PMI. Even if you didn't get all the algebra perfectly, you can still get lots and lots and lots of the points, like 16 out of 20 points, just by following, the basic steps, even if your algebra is poor. So there's no real reason not to do okay on proof by mathematical induction, because I do give so much partial credit for simply understanding the process. But what are the ways that we lose points on a proof by mathematical induction? Well, you can lose points by not telling your reader what your basis value is. You can lose points by starting with the left-hand side equals the right-hand side. That's a no-go. You'll definitely lose points if you don't say assume, P of K. You will lose points if you start your argument with the whole equation P of K plus 1. That's not a good idea. We can't start with what we wish to establish, but we can start with the left-hand side and work on it until it looks like the right-hand side, or at least the best of our ability. So you should be able to get a lot of partial credit on proofs by mathematical induction.
Professor, in
Uh-huh.
class, you
Uh-huh.
mentioned when writing the left-hand side to be, especially for k and k plus 1, to remember to use if, for example, if we're using I as our integer value, I equals 1 summation k, for example,
Yep.
to, in the left-hand side formula, use I and not k or k plus 1.
Yeah, let's talk about that. That is such a great point, Nora. Indexing variables versus upper limit variables. So glad you brought that up. So here's a caution. All right. Let's say we have the sum from I equals 1 to k, I don't know, of some expression. I'll say I squared plus 5i, for example. Okay. That would be a correct way to write, say, a left-hand side of a p of k, for example. It is not equal to the sum from I equals 1 to k of k squared plus 5i. Oh, or that either, but let's just say we put k here and k here. These are not the same thing.
Can I ask a question?
Uh-huh.
When you have k squared plus 5k, would that's considered the last term?
This is the last term. That's right. Because what this would be, I'll show you what that is too. You know, if we were going to expand this, it's, 1 squared, you could tell me, plus 5 times 1, right? Plus 2 squared, plus 5 times 2, plus keep on going. What would the last term look like now?
K squared plus 5 times k?
That's right. Whereas the sum from I equals 1 to k of k squared plus 5k is this written k times,
Oh,
which is k times k squared plus 5k, which is not the same thing as that.
so when we pop off the final value, we it, we would index for this, it would be I equals no, k minus 1 to k, because we do something
Oh,
with the
okay. Yeah, yeah, yeah,
indexing.
yeah. If we wanted to break off like the last term in this, it would go from I equals 1 to k minus 1 plus this.
Oh, okay.
Yeah, yeah, because you looked at that really interesting problem where the upper limit was n minus 1. In fact, it became n minus 2 when we broke off the last one. No, it became n because we were at n plus 1. Yeah, okay. We don't see those that often, right?
Okay.
But this is kind of an interesting, thing that happens a lot. This error of thinking, oh, I'm just gonna go right ahead and put the K in here. No, they're not quite the same. In fact, quite not the same.
But
Because,
for the right hand, I'm sorry.
no, you go ahead.
No, I was just saying for the right hand side, we do substitute our values because we're talking about specific, and well, not here, but when we're doing the induction and we have our left hand side where this is, and then we have our right hand side, which we're solving to, then we keep our values the same.
That's right. So breaking off the K plus first term or factor In a sum, it's a term. The sum from I equals 1 to k plus 1 of any expression. I'll just say a sub I. That could be any expression. It could be I squared plus 5i. It could be, any one of many expressions that we've seen. 1 minus 1 over I, 1 plus 1 over I. I mean, they look different ways, right? But this is the sum from I equals 1 to k of a sub I plus whatever that last term looks like, which means you're plugging in k plus 1 wherever you see an I. And if it's a product from I equals 1 to k plus 1 of, say, b sub I, it's the product from I equals 1 to k of that same expression b sub I times whatever the k plus first factor would look like when you plug the k plus 1 everywhere you see an I. So when I say a sub k plus 1, I'm saying whatever the expression, like if the expression for a sub I is this, we plug in a k plus 1 for I there, and we plug in a k plus 1 for I there. That's what we mean by the k plus first term.
Okay.
Does that make sense?
So we would write that expression with our substituted values.
Right. We could look at some examples.
Like if we're doing induction, we're working in pk plus 1 and we're doing induction, then we write the left-hand side expression with our variables and we add that to our p of k induction value.
That's right. Like I think we saw this one, and it equals 1 over n. This was that a product or a sum? I think no, this was a product. This was a product. Right. So P of k plus 1 looked like the product from I equals 1 to k plus 1 of 1 minus 1 over I equals 1 over k plus 1. But starting with, like you said, the left-hand side, we start with this and we break off that last factor. First, it's the product from y equals 1 to k of the same expression times, a sub k plus 1 is this expression, but with k plus 1 plugged in. So, this is our product from I equals 1 to k of a sub I times a sub k plus 1. This is the a sub k plus 1 term right there. If it's a product, if it's a sum, then there's a plus here.
So how did I get that? Like 1 over k plus 1.
1 minus 1 over k plus 1 by plugging in k plus 1 here into this expression. The a sub I expression is 1 minus 1 over I. That is the a sub I expression. That's a sub I. This whole thing right here is what we call a sub I. It's the term, the general term. It's a lot of times we're hunting for that formula for that, If it's a sequence, we're looking for that formula. So when we put in the highest value for I, which is k plus 1, into that I right there, we get this.
Okay.
Does that make sense?
Yeah.
And this is a times, not a plus. But, maybe if it's a sum formula like the sum from I equals 1 to n of I squared, that formula is n times n plus 1 times 2n plus 1 over 6. This is an interesting proof to try to prove. Did I do this one in class?
I think we had that for one of our WebAssigns not too long ago.
Yeah, I think that's the way that we looked at this one. But this one is the same thing, except it's a sum, not a product. Okay, so our sum from I equals 1 to k plus 1 of I squared, we could write it as the sum from I equals 1 to k of I squared plus k plus 1 squared. This is our a sub I, k plus 1, where, this is our sum from I equals 1 to k of a sub I. So whether, if it's a sum, there's a plus here. If it's a product, there's a times there. Between the first k, do whatever you're doing with them, either add them or multiply them, and then the broken off term will either be added or multiplied, depending upon whether it's a product or sum.
Mm.
Good.
This was really helpful. Thank you.
Well, what's really helpful is that you come to office hours and ask questions. That is the most helpful thing of all. So thank you always for coming and asking questions. Do you have any other questions before we call it a night? Sorry, I keep clinking my spoon here. I couldn't resist. I made a little fruit salad. I couldn't resist sneaking a bite. Well,
This is really challenging for me because there's so much information and there's so much back and forth on the two sides. I noticed that we spend a lot of time on the left-hand side. We look at the right-hand side for P of K because we're setting up the inductive hypothesis. But then for the left-hand side, we stay kind of focused on the left hand with A sub I and getting that value, the final value popped off so we can do our induction later. So we kind of stay on the left-hand side until we get down to the inductive step for P of K. And then we stay on the left-hand side until we try to set up our equality with the right-hand side of P of K plus 1.
and there is more than one way to play the game. It's just that a lot of times the right-hand side of P of K is so simple. There's no clue what you're supposed to do with it. Like, what do we actually do with 1 over k plus 1 that would help us get it to look like this? See what I mean?
Yeah.
I mean, well, we could take a guess and say, well, maybe I'll multiply this times k over k. That's legal. Or just be multiplying by 1. But how do we know that that's going to help us get to this? I hear exactly what you're saying. I totally hear what you're saying. The thing about it is, I mean, even this, yeah, this is fairly complicated right-hand side. But what are you going to do with this to get it to look like that? It's not at all clear what the steps are if you were trying to start with the right-hand side and move to the left-hand side. Whereas if we start with the left-hand side, we know, hey, or P of K, hey, I know what I can do with this, And this actually isn't all of P of K. I'm so sorry. This is only the left-hand side of P of K. This is only the left-hand side. The all of P of K plus 1 is actually the statement that the sum from I equals 1 to k plus 1 of I squared. Oh, I'm so glad you said that, because I would not be happy with myself if I left this without saying more. K plus 2 times k plus 1 over 6. This is actually P of k plus 1. This is just the left-hand side. Thank you so much, Nora. You actually corrected something there for me. All right, now it is true. There's more to do here. Like, we could say, okay, I can start working on this and I can distribute the 2. And in fact, I already did something. I already said k plus 1 plus 1. I actually already, kind of did that. Maybe I should erase that and put k plus 1 here, yes, sometimes there is work to be done on the right-hand side of P of k plus 1, right? Like, we can rewrite this. It actually, what is k plus 1 times k plus 2 times 2k plus 3. So that step you could take. But once you get that far, it's very unclear how to get to this. Whereas we have a sort of a real strategy for starting with the left-hand side, breaking off that last term, or in the case of a product, breaking off that last factor, performing the induction step where we perform the substitution, and then just look at what we get after that and then try to transform it into whatever this looks like. It seems easier. Now, I will say there is a whole class of problems that I decline to teach anymore. And those are the problems in section 5.3. You've probably looked at them because I know you look at the back of the book at the exercises at the end of each section. Not the back of the book, but the back of each section. And there are inequalities to prove. Have you noticed that some of the statements are inequalities?
Yeah, I hurried away.
Yeah, well, they're really fun. And your point comes to bear when you're trying to prove an inequality. A lot of times, if I'm trying to prove something is less than something or less than or equal to it, I'll work on this for a while and I'll work on this for a while, and make sure that as I work on this, it's either still less or less than or equal to, or just equal to. And in here, I would make sure it's greater than, greater or equal to, and then you can go whoop, and then you do actually take the work that you did here, you take the work that you did here, and you make your argument linear, but you actually use the two pieces if you're trying to prove an inequality. And that is the classic way to do it. A lot of times it's hard to kind of do it directly. You do work on this for a while and maybe work on this for a while and try to meet somewhere in the middle with a sequence of inequalities that work.
Why don't you teach it anymore?
Do you see what I'm up against? Trying to
Oh,
teach the simple stuff.
I see. I'm sorry.
Oh no, it's really depressing. Uh, because students wouldn't follow it. There would be so few students that would follow it that it would just frustrate people. Like people are having a hard enough time as it is just getting induction down. Induction involving inequalities would be more challenging than most of the people in the class would be able to handle. That's just my experience. What happened was here. We can go off. Well, actually, it's history. You should all know. The information technology major did not used to exist. In fact, in 1998, that was the last year, I believe, that the math majors and the computer science majors all sat in one class together, and it was a proofwriting class for math and computer science majors called discrete mathematics. At that stage of the game, the computer science students were such at a high level that they would sit in the same class with math majors. Around 98, we split the math majors off and we have our own class for math majors. It's called Introduction to Abstract Mathematics. It's a proofwriting course with, lots of concepts, very similar to what we're learning in discrete, but there are some differences. And it was computer science and what used to be called the Computer Information Systems major. And the CIS majors are now what are called the IS majors. I believe it was 2014 or 2015 when the IT major was brought onto the books. And that major, because the math requirements are so much lower than the math requirements for a comp sci major, which are Calc 1 and Calc 2, most students started taking the IT major because the math requirements are so much easier. So what we wound up getting was lots of students who weren't able to get, didn't feel able and probably weren't able because in high school they didn't take sufficient math to get through a calculus sequence, Calc 1 and Calc 2 here. So the IT major offered them a door into information sciences that was a different major program that was easier on the math side. But because now most of the people in our class that I teach are information technology majors and have weak math backgrounds, I have had to water down, as have we all, the content of this course considerably since I started teaching it in 2002. I try my best to pull everyone along the best that I can, but I do make compensations. Like 20 years ago, if somebody was working on a proof by mathematical induction and couldn't get the algebra to get from here to here, they would, earn maybe 8 out of 20 points or 10 out of 20. But for the group of students who struggle so much, I satisfy myself with, hey, do you know the basic structure? Do you know at least what you're supposed to be trying to do? Even if you can't actually do every little algebra step, you still get lots of credit for knowing, hey, I'm trying to prove P of k plus 1. Oh, I know at least I'm going to have to use the inductions hypothesis, so I'm going to have to break off a term so I can see how to use P of k. Like I try to give a lot of credit for that now. But there are other, kind of fundamental things that I no longer teach, certain proofs that I don't teach anymore, because students are going to really struggle. And that's why. Aren't you sorry you asked? But y'all should know the history of it, the IT major. But now, starting this last fall, you have to have 115. So if you started school before fall of 2024 and you're in the IT major, you don't have to have 115, math 115. But anybody who started the IT major fall 2024 or later will have to take math 115. And math 115 is a class that's algebra heavy. It is college algebra. And it's where you learn to do all of this stuff that maybe students are struggling with, factoring and exponents and, stuff like that.
I see.
Yeah. So there's a history there. I'm going to stop. But I'm so glad you came tonight. Thanks for listening.
This was so helpful. I really appreciate it. And the template for induction writing is just fantastic. Right before the material, the measure two material is great.
Oh, good. Oh, good. So I did put that up.
I didn't see the office hours that you guys were talking about. I saw Friday, the 16th and the 14th. I don't know. Maybe I missed it. I don't know.
Hang on. Let me look.
That's the one, the Friday 16. I'm 18.
Okay, so
I didn't see an 18th.
office hour notes from Friday the 16th. No, that's Wednesday. Oh, it's the 18th, Friday the 18th. Oh, but where are Monday's notes? What is today? Wednesday? Oh, nobody came
Today's the
Monday.
20th.
Nobody came Monday.
That's why I was like checking Monday note, but there wasn't Monday.
No,
No.
it's 418. 418.
There's no
Go ahead.
there's no 18 visible to me. Mine stops at 416.
What? Hang on. Did I not? What? Let me look. Office hour notes. Oh, oh my goodness. Well, let me get them up. How is it? They're up for the other class, but somehow oh, thank you so much. Because it's a whole lot of stuff that you want. Office hours. Oh, I don't know why they didn't get up. I'm gonna put them up right now. You tell me if they show up. I'm gonna put them up right now, and then you can refresh your screen. Hang on. Oh, thank you so much for telling me that. Sunita is in a different. She's in the Monday, Wednesday class, and so she was the only one that came. I guess I was tired that night. There's no excuse. All right, hang on. All right, they should be there now. If you refresh.
Yep, let me see. Yes, I see them. Thank you, Professor.
Oh no, thank you because I honestly didn't realize that. Okay, I'll get these up and we'll see you tomorrow.
All right. Have a great evening.
You too.
Bye, Professor.
Goodbye. Goodbye, Sunita.
Bye.
Have a good night.